If you have ever watched a classic science fiction film, you have almost certainly heard the word parsec used incorrectly. In pop culture, scriptwriters often confuse it with a unit of time, turning it into a flashy term for speed or rapid journeys across space. However, in the realm of actual astrophysics, a parsec has absolutely nothing to do with time. It is a fundamental, rigorous unit of distance. In fact, it is the primary ruler that professional astronomers use to map the vast expanse of our universe. One single parsec equals roughly 19.2 trillion miles, or over 30 trillion kilometers. That is a mind-boggling scale, yet the concept originates from a surprisingly simple geometric trick that you can recreate right now with your own hands. Today, we are going to explore parsec, the strange distance that makes no sense but holds the universe together. If you find this journey into deep space geometry fascinating, please consider liking this video and subscribing to the channel for more scientific explorations. We would also love to hear from you, so please leave a comment down below telling us where you are tuning in from and what time it is wherever you are on Earth right now. To truly understand how astronomers measure the incredible distances between stars, we first need to look inward at our own biology. The foundational trick behind calculating a parsec relies on a physical phenomenon known as parallax. You experience this phenomenon every single second of your waking life, without even realizing it. Human beings, along with many other predatory species on Earth, possess binocular vision. Our eyes are placed on the front of our faces, separated horizontally by an average distance of roughly 2.5 inches, or about 6.5 centimeters. This structural separation means that each eye views the world from a slightly different perspective. You can observe this fundamental mechanic with a remarkably simple demonstration. Hold your arm straight out in front of you and extend your thumb upwards. Close your left eye and look at your thumb with only your right eye, taking note of which distant background object your thumb appears to align with on the wall across the room. Now, without moving your hand or your head, switch eyes. Close your right eye and open your left eye. Suddenly, your thumb appears to jump horizontally across your field of view relative to the background wall behind it. Your thumb did not actually move through physical space. The apparent shift in position occurs entirely because your left eye views the thumb from an angle that is 2.5 inches away from your right eye. This apparent angular shift of an object against a distant backdrop when viewed from two different points is precisely what scientists define as parallax. Your brain is a masterful natural supercomputer that processes these two distinct images simultaneously. By calculating the slight angular difference between the image captured by your left retina and the image captured by your right retina, your visual cortex automatically triangulates the position of the target. Through this internal geometric calculation, your brain accurately estimates depth and spatial distance. If you bring your thumb closer to your nose and repeat the eye-swapping test, you will notice that the jump appears much larger. The angular displacement increases as the target object moves closer to the observer. Conversely, if you extend your arm as far away as possible, the jump becomes noticeably smaller. If you look at a distant mountain peak or a tall skyscraper miles away and alternate between your left and right eyes, you will perceive virtually no shift at all. The baseline distance between your eyes, 2.5 inches, is simply far too narrow to create a measurable angle against an object located so far away. This biological limitation poses a massive obstacle when human beings look up at the night sky. The stars, planets, and galaxies are located at mind-numbing distances across the cosmic vacuum. If you stand outside at night and close one eye, then open the other, the stars will not appear to move at all. The distance between your human eyes is fundamentally useless for triangulating the location of celestial objects. For centuries, ancient observers looked at the night sky and assumed that the stars were fixed upon a giant hollow crystal sphere that rotated around Earth. They could not detect any visual shift, which led many early thinkers to believe that the stars were all sitting at the exact same distance from our world. To overcome this boundary, early astronomers realized they needed a drastically wider baseline. 2.5 inches works well for catching a ball or navigating a dense forest, but measuring deep space requires a baseline on an astronomical scale. Humanity obviously could not build a physical telescope that was millions of miles wide, Nor could researchers easily set up synchronized observatories across vast oceans during the era before modern global communication. The brilliant breakthrough came when scientists realized that Mother Nature had already built the ultimate baseline for us. That baseline is the orbit of planet Earth around the Sun. As Earth travels along its orbital path, it sweeps through a massive ellipse in space. Earth sits on one side of the Sun during the month of January. 6 months later, in the month of July, Earth has completed one half of its annual journey around our host star. It now sits on the exact opposite side of its orbit. The physical distance between Earth's position in January and its position in July is approximately 186 million miles, or nearly 300 million kilometers. This immense diameter represents twice the distance between Earth and the Sun, a metric known in astronomy as 2 astronomical units. By utilizing Earth's planetary orbit, astronomers gained a gigantic virtual baseline. Imagine aiming a powerful space telescope at a relatively nearby star in the middle of January. You record its precise location against the backdrop of extremely faint, vastly more distant background galaxies. You then wait patiently for 6 full months while planet Earth carries your observatory across nearly 200 million miles of space. In July, you photograph the exact same star once again. Because your telescope has moved by a massive physical baseline, the position of that nearby star will appear to have shifted ever so slightly against the static background of distant galaxies. Just like your thumb shifted when you alternated eyes, the nearby star shifts position because you observed it from 2 radically different vantage points in the solar system. This orbital shift is called stellar parallax. It represents the master key that unlocked our true understanding of cosmic geometry. By measuring the precise angle of this tiny shift across 6 months, and knowing the exact distance of Earth's baseline, astronomers can apply basic high school trigonometry to calculate the absolute distance to that star with remarkable accuracy. However, applying this simple trigonometric concept to the reality of the cosmos proved to be one of the most grueling challenges in the history of science. The universe is so staggering in scale that even a baseline spanning nearly 300 million kilometers produces an angular shift so insanely microscopic that early human tools were completely incapable of detecting it. The stars are not miles away, nor are they millions of miles away. They are located trillions upon trillions of miles into the abyss, making the apparent shift almost invisible to the naked human eye. Scientists needed a far more precise system of angle measurement to capture these microscopic movements, which leads us directly into the mathematical origin of the parsec itself. To understand the mathematics behind the parsec, we must examine how astronomers measure angles across the night sky. In daily life, we divide a full circle into 360 degrees. A right angle contains 90 degrees, while the full circle surrounding your field of view stretches across 360 degrees. When you look at the full moon sitting on the horizon, it occupies a width of roughly half a degree in the sky. Half a degree might sound fairly small, but on the vast canvas of professional astronomy, half a degree is an enormous area. It is far too large to describe the tiny shifts observed in stellar positions. To measure microscopic structures across deep space, astronomers must divide degrees into far smaller subdivisions. Every single degree is divided into 60 equal parts called arc minutes, or minutes of arc. If you picture a single degree on the horizon and slice it into 60 identical segments, each slice represents 1 arc minute. The full moon, spanning half a degree, measures approximately 30 arc minutes across. Astronomers then take this precision a step further. They take a single arc minute and slice it into another 60 equal subdivisions. These microscopic divisions are called arc seconds, or seconds of arc. Therefore, 1 single degree contains 3,600 arc seconds. To grasp just how infinitesimally tiny 1 arc second is, consider a few real-world physical comparisons. If you place a standard American dime on the ground and walk away until you are located roughly 2.5 miles or 4 kilometers away from that coin, the width of that dime from your distant perspective spans an angle of precisely 1 arc second. Alternatively, picture a single human hair held at a distance of about 30 or 40 feet away from your eyes. The apparent width of that thin strand of hair corresponds to approximately 1 arcsecond of visual angle. When astronomers sit at their observatories and measure the subtle shift of a nearby star over a 6-month period, they are not tracking shifts measured in degrees or even arc minutes. The shift is so unbelievably tiny that it is measured in mere fractions of a single arcsecond. This brings us directly to the mathematical origin and etymology of the word parsec. The term is a portmanteau, a clever combination of two distinct scientific words, parallax and arcsecond. When you fuse the prefix of parallax with the suffix of arcsecond, you create the term parsec. The physical definition of a parsec is rooted entirely in pure right triangle trigonometry. Imagine a right-angled triangle spanning across deep space. The base of this imaginary right triangle is the distance between planet Earth and the Sun, which equals 1 astronomical unit, or roughly 93 million miles, which is nearly 150 million kilometers. The tip of the triangle extends outward to a distant star located far away in our galaxy. As Earth orbits the Sun, the angle formed at the distant star changes. The parallax angle, typically denoted in formulas by the letter P, is defined as half of the total apparent angular shift observed over 6 months. In other words, it is the angle subtended at the star by a baseline of exactly 1 astronomical unit. A parsec is defined as the precise distance at which a star would exhibit a parallax angle of exactly 1 arcsecond. If a star is sitting at a location in space where Earth's baseline of 1 astronomical unit creates an angle of precisely 1 arcsecond at the star, that star is sitting at a physical distance of exactly 1 parsec away from us. Because of the way right triangle trigonometry functions at extremely small angles, a simple mathematical relationship emerges. For very small angles, the tangent of an angle is virtually identical to the angle itself measured in radians. This geometric reality allows astronomers to bypass complex trigonometric equations and use a remarkably elegant formula to calculate distance. D equals 1 divided by P. In this streamlined equation, D represents the distance measured in parsecs, and P represents the parallax angle measured in arcseconds. The simplicity of this formula is precisely why astronomers created the parsec in the first place. If an astronomer measures a star's parallax angle to be 0.5 arcseconds, calculating the distance takes a split second. 1 divided by 0.5 equals 2, therefore the star sits at a distance of exactly 2 parsecs. If another star exhibits a microscopic parallax angle of 0.1 arcseconds, 1 divided by 0.1 yields 10, meaning the star is located 10 parsecs away. The larger the parallax angle, the closer the star sits to our solar system. The smaller the parallax angle, the farther away the star resides. As the distance to an object stretches toward infinity, its parallax angle shrinks closer and closer toward absolute zero. When you convert 1 parsec into standard daily measurement systems, the resulting numbers become staggeringly gigantic. 1 parsec equals approximately 3.26 light-years. In terms of linear distance, 1 parsec spans roughly 20.6 trillion miles, or 30.8 trillion kilometers. To put that in perspective, 1 single parsec is equal to more than 200,000 astronomical units. If you wanted to travel a distance of 1 parsec using humanity's fastest modern spacecraft, which travel at tens of thousands of miles per hour, the journey would take tens of thousands of years to complete. The nearest star system to our Sun, Alpha Centauri, is located about 1.3 parsecs away from Earth, which translates to roughly 4.2 light-years, or over 25 trillion miles. The elegance of the parsec lies in its absolute detachment from arbitrary human metrics. Meters, kilometers, feet, and miles were all invented based on human physical scales, earthbound geography, or arbitrary historic standards. Even the light year, while deeply rooted in physics through the speed of light, relies on the human concept of a year, which is merely the specific length of time it takes our specific planet to orbit our specific star. The parsec, by contrast, is a geometric relationship born from observation. It connects the physical size of our planetary orbit directly to the fundamental angular layout of the night sky. It allows scientists to calculate deep space distances using direct observation rather than relying on assumed physical speed parameters. However, deriving this mathematical clarity required centuries of astronomical struggle. Long before scientists could plug fractions of arcseconds into simple formulas, they had to prove that stellar parallax could be detected at all. For centuries, the inability to observe this microscopic angle stood as the single greatest argument against the idea that planet Earth moved through space. Long before astronomers established the parsec as a mathematical standard, the sheer inability to detect stellar parallax served as one of the most formidable scientific arguments against the structure of the solar system we know today. In ancient Greece, scholars such as Aristotle argued passionately for a geocentric model of the cosmos, placing a stationary Earth at the absolute center of the universe. Aristotle reasoned with sound geometric logic that if Earth moved in a path around the Sun, observers on Earth ought to see the fixed stars shift their relative positions across the sky throughout the year. Because no ancient scholar could detect even the slightest movement among the stars, Aristotle concluded that Earth must remain motionless at the center of all things. This objection persisted across centuries and resurfaced with immense force during the Renaissance. When Nicholas Copernicus published his heliocentric model in the 16th century, proposing that Earth and the other planets revolved around the Sun, critics immediately raised the ancient parallax paradox. If Earth was hurtling through millions of miles of space every year, why did the constellations remain rigidly unchanged? Copernicus offered a radical counter-argument. He suggested that the stars were simply vastly farther away than anyone had ever dared to imagine. He argued that the distance to the stars was so vast that the resulting parallax angle was far too minuscule to be detected by the human eye or the instruments of his era. Decades later, the famous Danish astronomer Tycho Brahe attempted to settle the debate using the most precise pre-telescopic instruments ever created. Brahe built massive quadrants and sextants capable of measuring celestial angles with unprecedented accuracy. Yet, despite his incredible technical precision, Brahe failed to detect any stellar parallax. Because he could not conceive of a universe so immense that stellar parallax would fall below his observational limit, Brahe rejected the full Copernican model and devised a hybrid system instead. The invention of the telescope in the early 17th century changed everything, but measuring stellar parallax remained an elusive, maddening target. Even with magnifying lenses, early telescopes suffered from severe optical distortions, chromatic aberration, and unstable mounting systems. Furthermore, atmospheric turbulence caused star images to flicker and blur, smearing microscopic points of light into fuzzy blobs that completely masked tiny angular movements measured in arcseconds. As telescope design improved during the 18th century, astronomers kept searching for parallax, often stumbling upon other profound physical phenomena while failing to achieve their original goal. James Bradley, an English astronomer searching for stellar parallax in the 1720s, continuously observed subtle circular shifts in the apparent positions of stars. However, these shifts did not match the geometric pattern expected from orbital parallax. Instead, Bradley had accidentally discovered the aberration of light, a phenomenon caused by the finite speed of light combined with Earth's orbital motion. While Bradley failed to measure parallax, his discovery provided the first direct observational proof that Earth moved through space. By the early 19th century, telescope technology had advanced to the point where measuring stellar parallax finally slipped within human reach. The key breakthrough arrived with the development of the heliometer, a specialized telescope featuring an objective lens split precisely in half. By sliding the two lens halves relative to one another, astronomers could bring the images of two nearby stars into exact alignment, allowing for angular measurements of astonishing precision. By the 1830s, the race to measure the first stellar parallax became the ultimate prize in global astronomy. Three legendary astronomers working in different parts of the world independently targeted three different stars, each employing distinct observational techniques. In Russia, Friedrich Georg Wilhelm von Struve focused his powerful telescope at the Pulkovo Observatory on Vega, one of the brightest stars in the northern sky. Struve reasoned that bright stars were likely closer to Earth than faint ones, making them ideal candidates for exhibiting measurable parallax. By 1837, Struve published preliminary measurements suggesting a parallax angle for Vega, though his early calculations contained significant uncertainties. Meanwhile, in South Africa, Scottish astronomer Thomas Henderson targeted Alpha Centauri at the Royal Observatory at the Cape of Good Hope. Henderson recognized that Alpha Centauri possessed a large proper motion. It moved noticeably across the sky over time relative to background stars. A large proper motion strongly implied that a star was located relatively close to our solar system. Henderson gathered extraordinarily precise data between 1832 and 1833 that clearly revealed a parallax shift. However, lacking confidence in his instruments and fearing error, Henderson delayed publishing his results for several years. While Henderson hesitated, German mathematician and astronomer Friedrich Wilhelm Bessel took a meticulous, systematic approach at the Königsberg Observatory. Bessel chose a faint star, known as 61 Cygni. While 61 Cygni was unremarkable to the naked eye, it displayed an extraordinarily fast proper motion, sprinting across the celestial background faster than almost any other star known at the time. Bessel reasoned that 61 Cygni's rapid motion across space was a clear giveaway of proximity. Using a masterfully constructed Fraunhofer heliometer, Bessel observed 61 Cygni painstakingly, night after night, for over a year. He meticulously controlled for temperature fluctuations, mechanical wear, atmospheric refraction, and instrument tilt. In late 1838, Bessel published his definitive results. He announced that 61 Cygni exhibited a parallax angle of approximately 0.314 arcseconds. Bessel's announcement sent shockwaves through the scientific community. For the first time in human history, someone had measured the precise distance to a star beyond our Sun. Using the trigonometric relationships that would later define the Parsec, Bessel calculated that 61 Cygni was located approximately 10.3 light-years away, a distance spanning tens of trillions of miles. Shortly after Bessel's publication, Henderson published his measurements for Alpha Centauri, and Struve finalized his work on Vega. All three astronomers had successfully shattered the boundary of our solar system within months of each other, but Bessel earned the historic honor of being the first to publish definitive proof. The successful measurement of stellar parallax in 1838 transformed astronomy forever. It finally settled the centuries-old debate started by Aristotle and Copernicus, providing undeniable physical proof of Earth's motion through space. More importantly, it provided humanity with its first true spatial tape measure, revealing that the stars were not mere points of light pinned to a local dome, but vast suns scattered across a terrifyingly immense abyss of space. As observational techniques refined over the following decades, astronomers required a standardized professional unit to handle these microscopic arcsecond measurements smoothly, setting the stage for the formal introduction of the parsec in the early 20th century. Outside of professional scientific institutions, the light year reigned supreme as the most famous unit of cosmic distance. Popular literature, science fiction novels, documentaries, and educational textbooks regularly rely on the light year to convey the scale of the universe. It is an exceptionally intuitive concept for the general public. Defined as the physical distance that a particle of light travels through a vacuum in 1 Julian year, a light year connects space directly to time. Because light travels at a constant velocity of roughly 186,000 miles per second, or nearly 300,000 kilometers per second, expressing distances in light years provides an immediate mental picture of look-back time. When we say a star is 100 light-years away, the audience instantly understands that the light striking our eyes left that star a century ago. Despite its immense narrative appeal and conceptual clarity, professional astronomers almost exclusively utilize the parsec in their peer-reviewed papers, observational databases, and mathematical models. This choice is neither snobbery nor arbitrary convention. The preference for the parsec stems from deep practical advantages in observational geometry, data acquisition, and mathematical efficiency. The primary reason astronomers prefer the parsec over the light year is that the parsec is a unit derived directly from raw observational measurement. When an astronomer sits at a telescope to map stellar locations, the instrument does not measure time, nor does it directly measure physical distance in miles, kilometers, or light years. The telescope measures a physical angle on the sky expressed in arcseconds. If an observational researcher calculates a stellar parallax angle of 0.2 arcseconds, converting that observation into light years introduces an unnecessary artificial intermediate step. To calculate the distance in light years, the researcher would first have to compute the inverse of the parallax angle to find the baseline distance, and then multiply that figure by the conversion factor of 3.26156. This extra calculation adds unnecessary computational steps to massive datasets containing millions of stars. With the parsec, the raw mathematical translation is instantaneous. The formula d equals 1 divided by p requires no conversion factors, no physical constants, and no extra steps. The angle measured in arcseconds converts directly into parsecs through simple division. The parsec is, in essence, the natural language of observational trigonometry. It represents distance expressed in the exact geometric units in which the observational data was originally collected. Furthermore, the light year is inherently tied to a physical constant that must be defined independently, the speed of light. While the speed of light in a vacuum is a fundamental constant of modern physics, defined as precisely 297,924,580 meters per second, linking spatial measurements to light travel time introduces conceptual complications when processing purely geometric observations. Historically, before the speed of light was defined with absolute atomic precision in the late 20th century, estimates of light speed fluctuated slightly as experimental measurement techniques improved. If astronomical distance standards had been defined strictly around the speed of light during the 19th century, every refinement in the measured speed of light would have subtly altered the calculated distances to every distant star in the sky. The parsec, by contrast, is anchored to the physical geometry of our solar system and basic Euclidean trigonometry. It remains immune to variations in light speed metrics because it is a direct statement of angular ratio. Another critical advantage of the parsec involves the mathematics of intrinsic stellar properties, particularly absolute magnitude. In astrophysics, understanding a star requires knowing its true intrinsic brightness, known as its absolute magnitude, rather than just how bright it appears from Earth, known as its apparent magnitude. A remarkably bright star located extremely far away might look identical in the night sky to a dim star sitting right in our cosmic backyard. To compare stars on an equal footing, astronomers created a standard formula that calculates how bright any star would appear if it were placed at a fixed, standardized reference distance from Earth. That standard reference distance was defined by international agreement to be precisely 10 parsecs. The mathematical equations that link apparent magnitude, absolute magnitude, and distance are known as the distance modulus equations. When distance is measured in parsecs, these equations take on an exceptionally elegant logarithmic form. The distance modulus is expressed simply as apparent magnitude minus absolute magnitude, which equals 5 times the logarithm of the distance in parsecs minus 5. If astronomers attempted to use light years in the standard distance modulus equation, the formula would require awkward fractional offsets and messy conversion constants. By anchoring the definition of absolute magnitude directly to 10 parsecs, the entire mathematical framework of stellar astrophysics becomes streamlined, reducing computational overhead and minimizing the risk of rounding errors in large sky surveys. The parsec also eliminates subtle linguistic and cultural confusion surrounding time measurements. A year is defined by Earth's orbital period around the Sun, which lasts approximately 365.25 days. However, different academic disciplines and historical calendars have utilized slightly different definitions of a year, such as tropical years or sidereal years. While the International Astronomical Union officially standardizes the light year using the Julian year of 365.25 days, relying on time units to express spatial dimensions remains conceptually redundant for observational cartography. The light year remains a brilliant pedagogical tool for science communication. It excels at explaining the finite speed of cosmic signals and reminding the public that looking deep into space means looking backward through time. But inside the observatory, where researchers process terabytes of sky survey data, compute orbital mechanics, and map out three-dimensional galactic coordinates, the Parsec remains the undisputed king. It connects the angle seen through the lens directly to the physical structure of space, serving as a pure, unadulterated geometric metric designed by observers for observers. As astronomers ventured beyond our immediate stellar neighborhood, they quickly realized that a single parsec, despite spanning over 19 trillion miles, was far too small a unit to comfortably describe the colossal structures of the deeper universe. Expressing the scale of our galaxy, or the distance to surrounding star systems in basic parsecs, rapidly leads to unwieldy numbers with endless zeros. To solve this problem, astronomers adopted standard metric prefixes, scaling the parsec upward by powers of 10 to create a set of exponentially larger cosmic tape measures, the kiloparsec, the megaparsec, and the gigaparsec. The first major step up the cosmic scale is the kiloparsec, abbreviated as KPC. 1 kiloparsec represents precisely 1,000 parsecs, which equals roughly 3,260 light-years, or over 19 quadrillion miles. The kiloparsec is the ideal unit for mapping structures within our own galaxy, the Milky Way, as well as our immediate galactic neighborhood known as the local group. To visualize the scale of a kiloparsec, consider the dimensions of our home galaxy. The Milky Way is a vast, rotating spiral disk composed of hundreds of billions of stars, interstellar gas, and cosmic dust. The overall diameter of this galactic disk spans approximately 30 to 35 kiloparsecs from edge to edge. Our solar system does not sit at the center of this cosmic wheel, nor does it sit at the absolute outer edge. Instead, planet Earth resides roughly 8 kiloparsecs, or about 26,000 light-years, away from the galactic center. When radio astronomers peer through dense clouds of interstellar dust to study Sagittarius A star, the supermassive black hole lurking at the heart of our galaxy, they express its location using kiloparsecs. Similarly, the majestic spiral arms of our galaxy, such as the Orion arm, in which our Sun resides, stretch across several kiloparsecs. Globular clusters, dense spherical swarms containing hundreds of thousands of ancient stars that orbit the halo of the Milky Way, are typically scattered at distances ranging from a few kiloparsecs to over 50 kiloparsecs away from the galactic core. The Magellanic Clouds, two dwarf satellite galaxies caught in a gravitational dance with the Milky Way, sit roughly 50 to 60 kiloparsecs from Earth. However, when we look past our local galactic halo and gaze into the vast abysses of intergalactic space, even the kiloparsec becomes insufficient. For these mind-boggling expanses, astronomers scale up by another factor of 1,000 to use the megaparsec, abbreviated as MPC. 1 megaparsec equals 1 million parsecs, which translates to roughly 3.26 million light-years, or over 19 quintillion miles. The megaparsec is the fundamental unit used to measure the distances between individual galaxies and map the large-scale architecture of galaxy clusters. For example, our nearest major galactic neighbor, the Andromeda Galaxy, is located approximately 0.78 megaparsecs away from Earth, or roughly 2.5 million light-years. Andromeda is currently hurtling toward the Milky Way, and the two massive galaxies are projected to merge into a single elliptical galaxy in a few billion years across a gap currently spanning less than 1 megaparsec. On the scale of megaparsecs, galaxies are rarely found isolated in empty space. Instead, gravity draws them together into bound galactic groups and dense clusters. Our own local group, which contains the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies, spans a total diameter of roughly 3 megaparsecs. Beyond our local group lies the Virgo cluster, a massive concentration of over 1,000 galaxies sitting approximately 16.5 megaparsecs away. When astronomers assemble groups of clusters into even larger associations, they define superclusters, which stretch across tens to hundreds of megaparsecs. The Laniakea supercluster, a titanic, gravitationally bound structure that includes our own Milky Way alongside more than 100,000 other galaxies, spans an astounding physical width of roughly 160 megaparsecs. To reach the ultimate boundary of observable reality, astronomers step up to the largest standard unit of distance in science, the gigaparsec, abbreviated as GPC. 1 gigaparsec represents 1 billion parsecs, which equals roughly 3.26 billion light-years, or a staggering 19 sextillion miles. The gigaparsec is used exclusively when mapping deep cosmological structures and calculating the physical properties of the observable universe as a whole. At the scale of multiple gigaparsecs, individual galaxies and clusters cease to look like distinct objects. Instead, the matter in the cosmos begins to resemble a vast, interconnected network known as the cosmic web. The cosmic web is the largest coherent structure in existence. It consists of delicate filaments of dark matter and luminous gas stretching across gigaparsecs of space, intertwined like the threads of a giant three-dimensional spiderweb. Where these massive filaments intersect, enormous galaxy clusters form. In between these filaments lie colossal regions of almost pure emptiness, known as cosmic voids. These voids are vast bubbles of space containing virtually no galaxies, stretching across tens to hundreds of megaparsecs in diameter. When modern space observatories conduct deep sky surveys, mapping hundreds of millions of distant galaxies, quasars, and active galactic nuclei, they plot these celestial objects on a grid measured in gigaparsecs. The radius of the entire observable universe, the spherical boundary from which light has had enough time to reach Earth since the Big Bang, is currently estimated to be approximately 14.3 gigaparsecs, or roughly 46.5 billion light-years in any direction. This expansion of scale reveals a profound aspect of the parsec's utility. What began as an extremely delicate microscopic angle measured from Earth's orbital movement around the Sun scales smoothly upward to measure the grandest structures in creation. The exact same geometric unit that allows us to calculate the distance to a single star sitting just past our solar system, when multiplied by 1 billion, allows us to map the cosmic web, quantify the size of the observable universe, and chart humanity's place within an ocean of space that spans billions of gigaparsecs. Yet, as we peer further into these multi-gigaparsec depths, measuring angles directly becomes completely impossible, forcing scientists to construct a sophisticated system of indirect measurement known as the cosmic distance ladder. Direct trigonometric parallax is an extraordinarily reliable tool, but it suffers from a fundamental, insurmountable physical limitation. As distance increases, the parallax angle shrinks toward absolute zero. At a distance of 100 parsecs, the parallax angle drops to a microscopic 0.01 arcseconds. At 1 kiloparsec, it shrinks to 0.001 arcseconds. By the time you look toward objects sitting 1 megaparsec away, the theoretical parallax angle collapses to 1/millionth of an arcsecond. Measuring an angle that small is equivalent to trying to resolve the diameter of an atom held at arm's length. Even with the most advanced optical mirrors, laser interferometers, and space telescopes operating outside Earth's atmosphere, measuring direct geometric parallax beyond our local region of the Milky Way becomes physically impossible. To map objects sitting millions or billions of parsecs away, astronomers could no longer rely on simple trigonometry. Instead, they had to invent an ingenious sequence of overlapping measurement techniques known as the cosmic distance ladder. The fundamental principle behind this ladder is simple. Each rung relies on the calibration of the rung below it. If the bottom rung is flawed, the entire structure collapses. And at the absolute foundation of this entire cosmic ladder sits the trigonometric parsec. To climb past the physical limits of direct parallax, scientists needed a way to determine the absolute physical distance to distant celestial objects without measuring angles. They accomplished this by identifying standard candles. In astronomy, a standard candle is a class of astronomical objects that possesses a known, predictable intrinsic brightness or true wattage. Imagine standing on a pitch-black plain at night. In the far distance, someone turns on a standard light bulb. If you already know for a fact that the bulb is rated at precisely 100 watts, you can easily determine how far away that person is standing. You simply measure how dim the light appears from your perspective. Because light spreads out in 3 dimensions according to the inverse square law, diminishing in intensity proportionally to the square of the distance, comparing the known intrinsic brightness to the observed apparent brightness reveals the exact physical distance to the light source. The most famous early standard candles were Cepheid variable stars. In the early 20th century, astronomer Henrietta Swan Leavitt made a groundbreaking discovery while analysing photographic plates of the Magellanic Clouds at the Harvard College Observatory. Leavitt noticed a peculiar group of giant stars that pulsated rhythmically, brightening and dimming over cycles lasting from a few days to several months. Leavitt discovered a direct, mathematically rigid relationship between a Cepheid star's pulsation period and its true intrinsic luminosity. A Cepheid that pulsates slowly over a 60-day cycle is intrinsically far brighter than a Cepheid that pulsates rapidly over a 3-day cycle. This discovery, known as the period luminosity relationship or Leavitt's law, meant that simply timing how long a Cepheid star takes to complete one pulse cycle reveals its exact intrinsic wattage. However, Leavitt's law only provided relative brightness. To convert these pulsation periods into absolute physical distances in parsecs, astronomers needed to anchor the system. They used direct trigonometric parallax to measure the exact distances to a handful of Cepheid variable stars located relatively close to Earth within our own galaxy. Once those local Cepheids were measured directly in parsecs, the entire class of stars was calibrated. In the 1920s, Edwin Hubble pointed the massive 100-inch Hooker telescope at Mount Wilson toward what was then called the Andromeda Nebula. Within its faint spiral arms, Hubble identified several Cepheid variable stars. By measuring their pulsation periods, calculating their intrinsic brightness, and comparing it to their apparent faintness, Hubble calculated that Andromeda sat far beyond the borders of the Milky Way, at a distance of nearly 1 megaparsec. In a single stroke, calibrated standard candles proved that our galaxy was merely one island universe among billions scattered across the cosmos. As brilliant as Cepheid variables are, they have their own distance boundary. Beyond 20 to 30 megaparsecs, individual Cepheid stars become too dim and crowded for even space telescopes to distinguish clearly from surrounding starlight. To reach into the gigaparsec regime, astronomers needed an immensely brighter standard candle. They found it in one of the most violent events in the universe, Type Ia supernovae. A Type Ia supernova occurs in a binary star system containing a white dwarf, the superdense core of a dead low-mass star. If the white dwarf gravitationally siphons gas from its companion star, it steadily accumulates mass until it hits a fundamental physical threshold known as the Chandrasekhar limit, which equals roughly 1.4 times the mass of our Sun. When a white dwarf hits this exact mass threshold, electron degeneracy pressure fails, triggering a runaway thermonuclear explosion that completely obliterates the star in seconds. Because every Type Ia supernova involves a white dwarf exploding at almost the exact same physical mass threshold, these stellar detonations detonate with remarkably uniform peak brightness. For a few brief weeks, a single Type Ia supernova shines with the combined light of over 5 billion suns, outshining its entire host galaxy. Because Type Ia supernovae are so outrageously bright, astronomers can observe them across gaps spanning hundreds of megaparsecs and several gigaparsecs. To calibrate these cosmic explosions, scientists search for rare intermediate galaxies that host both Cepheid variable stars and a Type Ia supernova. By using Cepheids to measure the exact distance to the host galaxy in megaparsecs, they determine the precise intrinsic peak brightness of the supernova. Through this chain of calibration, the cosmic distance ladder stretches across the entirety of observable space. Trigonometric parallax measures local stars directly in parsecs. Those local stars calibrate Cepheid variables, extending our reach to nearby galaxies in megaparsecs. Those Cepheids then calibrate Type Ia supernovae, extending our vision across thousands of megaparsecs into the gigaparsec realm. This interlocking system highlights why the parsec remains the ultimate bedrock of modern observational cosmology. Every calculation of the age, scale, and structure of the universe relies on this chain of measurement. If our initial trigonometric parsec calibrations at the bottom of the ladder contain subtle errors, those errors propagate upward, distorting our estimates of galactic distances, dark energy, and the total size of the observable universe. But as scientists built better instruments to refine that bottom rung, they uncovered a disturbing mathematical discrepancy at the top of the ladder, a friction in modern physics centered directly on the megaparsec. As humanity refined its spatial measurements from local stars to distant galaxy clusters, the parsec transitioned from a simple tool for surveying local stars into the cornerstone of modern observational cosmology. Today, the megaparsec sits at the very heart of one of the most intense, compelling controversies in modern physics. This debate does not revolve around whether space is expanding, but rather how fast that expansion is occurring, a rate expressed in a complex compound unit, kilometers per second per megaparsec. Understanding this unit is essential for grasping why modern cosmologists find themselves facing a profound, unresolved paradox. The rate of cosmic expansion is quantified by a parameter known as the Hubble constant. The unit, kilometers per second per megaparsec, describes how rapidly a distant galaxy appears to recede from an observer based on its distance in space. If the Hubble constant is estimated to be 70 kilometers per second per megaparsec, this means that for every additional megaparsec of distance separating an observer from a galaxy, that galaxy appears to move away at an additional speed of 70 kilometers per second. A galaxy located 1 megaparsec away moves away at 70 kilometers per second, while a galaxy sitting 10 megaparsecs away recedes at 700 kilometers per second. For decades, determining the precise value of this expansion rate was the central goal of observational astrophysics. In recent years, technological leaps allowed scientists to measure this value with extraordinary precision, expecting different measurement techniques to converge on a single, unanimous number. Instead, the opposite occurred. As measurement margins of error shrank, two premier methods of calculating the Hubble constant began to yield distinctly contradictory results, creating a major discrepancy known in scientific literature as the Hubble Tension. On one side of this debate is the late universe approach, which relies directly on the local cosmic distance ladder, calibrated by trigonometric parsecs. To make this ladder as accurate as possible, the European Space Agency launched the Gaia Space Observatory. Floating in space, Gaia was designed to measure the stellar parallax of over 1 billion stars with unprecedented precision, achieving measurement accuracies down to a few micro-arcseconds. A micro-arcsecond is 1/1,000,000th of an arcsecond, an angle so infinitesimally small that it corresponds to measuring the diameter of a human hair situated thousands of miles away. Using Gaia's ultra-precise parallax measurements, researchers anchored the local distances to Cepheid variable stars within the Milky Way with extreme rigor. By combining these calibrated Cepheids with observations of Type 1a supernovae in host galaxies, teams such as the SHOES project, led by Nobel laureate Adam Rees, derived a local expansion rate of approximately 73 to 74 kilometers per second per megaparsec. The statistical error margin on this local measurement was reduced to around 1%, representing an astonishing triumph of empirical observation. However, a serious conflict arises when researchers measure the expansion rate using an entirely different method, looking at the early universe. Rather than building a physical ladder step by step using stars and supernovae, cosmologists can analyze the cosmic microwave background, which is the remnant thermal radiation left behind roughly 380,000 years after the Big Bang. Space observatories such as the Planck satellite mapped the microscopic temperature fluctuations in this primordial background radiation across the entire sky. By applying the standard model of cosmology, known as the lambda cold dark matter model, scientists can project how these early radiation patterns should evolve across billions of years of cosmic history. This cosmological framework predicts what the expansion rate of the universe ought to be today. The results derived from the cosmic microwave background yield a Hubble constant of approximately 67 to 68 kilometers per second per megaparsec, accompanied by similarly tight statistical error margins. Here lies the fundamental puzzle. The local distance ladder approach suggests an expansion rate near 74 kilometers per second per megaparsec, whereas the early universe model predicts a rate near 68 kilometers per second per megaparsec. While a difference of 6 kilometers per second per megaparsec might initially sound minor, the extreme precision of both datasets makes this gap statistically significant. The probability that this discrepancy is merely a random statistical fluke is estimated to be less than 1 in 3 million, crossing the rigorous 5 sigma threshold that physicists require to claim a genuine discovery or crisis. Scientists approach this tension with extreme caution, employing careful hedging language because the true source of the discrepancy remains unproven. Broadly speaking, the scientific community is split between two primary hypotheses, neither of which has been definitively established. The first hypothesis posits that the disagreement may stem from subtle, unidentified systematic errors in observational data or instrument calibration. In any complex multi-step experiment, minor systematic biases can quietly compound. For instance, researchers hypothesize that stellar crowding, where neighboring stars blur together in dense galactic regions, might cause Cepheid variables to appear slightly brighter than they actually are, subtly distorting distance calculations. Other potential sources of error include unaccounted atmospheric or interstellar dust extinction, slight zero-point calibration shifts in space telescope sensors, or subtle variations in the chemical composition of stars across different galaxies. If systematic uncertainties exist within either the local distance ladder or the cosmic microwave background instruments, correcting those errors might eventually bring the two numbers into peaceful agreement without requiring new physics. The second, far more radical hypothesis suggests that both measurement teams are entirely correct. If the observations and their calibrations are flawless, then the discrepancy could indicate that the standard model of cosmology is incomplete. Researchers theorize that unknown physical phenomena might have altered the expansion rate of space over cosmic time in ways current models do not account for. Potential theoretical candidates include early dark energy, a hypothetical form of dark energy that may have exerted a transient push in the early universe, or exotic particles such as sterile neutrinos, evolving dark energy density, or modified theories of gravity that operate differently on cosmological scales. To resolve this tension without bias, astronomers are actively developing independent cross-validation methods. The James Webb Space Telescope is currently providing unprecedented infrared resolution, allowing researchers to re-examine individual Cepheid stars and alternative standard candles such as tip of the red giant branch stars with extreme clarity. Concurrently, astrophysicists are developing completely independent cosmic rulers such as gravitational wave standard sirens. When ultra-dense binary neutron stars collide, they emit both gravitational waves and electromagnetic radiation. By measuring the wave amplitude, scientists can derive direct geometric distances to distant galaxies without relying on Cepheid variables or supernovae. The debate surrounding the Hubble constant demonstrates the rigorous nature of modern science. Rather than sweeping minor discrepancies under the rug, astrophysicists treat this discrepancy in kilometers per second per megaparsec as a potential gateway to new discovery. Whether the resolution ultimately comes down to refining the calibrations of our local parsec baseline or revising our fundamental theories of dark energy and cosmic evolution, the megaparsec remains the arena where these profound cosmological questions are contested and ultimately answered. What began as a simple trigonometric trick has transformed into humanity's grandest spatial ruler. The parsec is far more than a mere technical definition or a convenient unit in an astrophysical database. It represents a profound bridge connecting human biological perception to the grandest architecture of the observable cosmos. Through a brilliant leap of geometric intuition, early thinkers realized that we could turn our planet's relentless journey around the Sun into an immense cosmic surveyor's wheel. By leveraging our 200 million-mile orbital baseline to measure the microscopic shift of a single arc-second, we unlocked the true dimensions of deep space. This single geometric relationship allowed humanity to step out of the dark, dismantling the ancient illusion that the stars were mere ornamental lights fixed to a local sphere. The parsec proved that we live in a dynamic, breathtakingly vast universe, providing the fundamental calibration needed to build the cosmic distance ladder. From measuring the proximity of neighboring stars to mapping the intricate web-like strands of galaxy superclusters across gigaparsecs, the parsec has served as our guiding light through the dark abyss. Even today, as modern cosmologists grapple with the Hubble tension, the megaparsec sits at the very frontier of human knowledge. Whether this paradox eventually exposes subtle limits in our instruments, or reveals entirely new physical laws governing dark energy and cosmic expansion, it is through this precise geometric metric that we continue to challenge and refine our understanding of reality. On a philosophical level, the parsec offers a humbling perspective on our place in creation. Our species exists on a tiny rocky world, orbiting an ordinary star, trapped within a fleeting human lifespan. Yet, through the power of mathematics, optics, and scientific curiosity, our minds have reached out across trillions of miles to measure the universe itself. The parsec reminds us that while we may be physically insignificant against the staggering backdrop of space, our capacity to observe, calculate, and comprehend the cosmos is boundless. Thank you for embarking on this deep journey through space, time, and geometry with us today. If you enjoyed this exploration of the parsec and the mechanics of cosmic measurement, please hit the like button and subscribe to the channel for more deep dives into the mysteries of our universe. Do not forget to drop a comment below letting us know where on Earth you are watching from today and what time it is in your corner of the world. Until next time, keep looking up at the stars, and remember that every microscopic angle holds a story spanning light years across the cosmos.